So in our group, we are developing new methods, efficient methods, starting from the faculty developed an idea of Gibbs-Duham integration to get the phase boundaries to the Fourier coefficients, and now we are extending these kind of like efficient methods to solid states. So we are trying to get the free energies for the solid states. So the idea of like molecular simulation, it actually spans a lot multidisciplinary like area like material science, nuclear engineering, and even civil engineering. And now we can try to apply this in our department as well. So the motivations here is that the thermodynamic stability is very important for many technological aspects, including making a prediction of the crystal structure, the most stable phases, determining the boundary between different phases. So it's actually needed to have very accurate estimation of the free energy of the solid phases, especially nowadays, like the first principle calculations, like density functional theory and others. They are now very expensive. So implementing those methods to a quantity that is already very expensive to compute, which is the free energy, is actually a challenging problem. So in our group, we are developing a method actually to try to tackle this problem. So just as an introduction, we know that from thermodynamics, we have the Gibbs free energy, which is a function of temperature and pressure. So we almost like compute what's called Helmholtz free energy, and later on we compute the pressure and add it in this form. So we don't compute the entropy like in this form, but what we are computing is Helmholtz free energy, and we're adding the work term here. So from statistical mechanics, the free energy is defined as like minus kT log of the partition function Q, and the partition function Q has two contributions. One of them is just analytical, it's called the kinetic contribution, and the other one is called the configurational part, which is actually the things that we are measured in simulation, and it ends up to be in this formula, which is very hard to compute. So it's just integration of the whole phase space. So if you have molecule, so you will get like center of mass like positions, and you will get the orientation of each molecule. So what we are interested in is to compute this configurational partition function. So this is multidimensional problem, so you can't just make it as a numerical integration, and it's almost impossible. And these kind of quantities like free energy and entropy, they are called thermal quantities. Thermal quantities, you cannot directly measure them in simulation.